Good evening. Guess I scared everybody away today, huh? I know I can't be my breath with this thing, so I don't know. Must be the test, must be the test. I brought the test back, so I have those for everybody. And I made some keys, but I guess I don't need so many of them now. Let's see. What's the last name again? Next time I'll remember for sure. Took the test, right? Okay. All right, well, unfortunately, we're in a situation where the overhead projector here, if I turn it on, it turns off the camcorder and the people online can't see. But what I'll do is I'll put some of these problems up on the board and we go over them just a little. Online, feel free to interject questions or requests as you want. Here's some, just sort of the short of the test. I'll put this on T2L also. We have this one, find the mass of the solid if the density function delta of x, y, z, it's in free space, depends only on y though, so we'll say it's y. Is over the solid below surface z equals 4 minus x squared minus y squared in octave 1. So I think it really helps to draw this. This surface is an upside down circular paraboloid, right? We recall that if we take z equals x squared plus y squared, it looks like this, right? Maybe from calculus 3, it goes up forever, but here's z equals x squared plus y squared. It's got circular cross sections here because the cross sections here, if you put z equals a constant, you've got a constant equals x squared plus y squared. Well, that's a circle. So it's got circular cross sections this way. If you put a cross section this way, putting, let's say x equals 0, then within here, this one is z equals 0 squared plus y squared. Oh, it's a parabola. So you get parabolas this way. And similarly, you get parabolas this way by going in the y equals 0 plane. So y equals 0, you get the parabola z equals x squared. So parabolas, and circles. It's a circular paraboloid. You can sketch some exact traces here, but we don't need to for this application. Now, what does this one look like? Well, if you put minus x squared plus y squared, it turns it upside down, and then you add 4 and it slides it up 4 units. So it's this one upside down and turned up, slid up 4 units. Looks like that. So z equals 4 minus that circular parabola. So this is actually still a circular parabola. It's just upside down and translated. And what is this trace then in the xy plane? Well, this you get by putting z equals 0, right? This is the z equals 0 plane that it's sitting in. So this must be 0 equals 4 minus x squared minus y squared. Equivalently, x squared plus y squared equals 4, right? Which is a circle of radius 2. So now I know a lot about this. I know this is the disk of radius 2, is the projection region. So now if I want to find the mass, recall, but let me know if you can't see very well. I'm kind of over on the side here. And the mass is the triple integral of the density over the solid. W, let's call it. I call this W. And well, let's see. That's I did this in cylindrical coordinates, thinking that would be easier, and I think it is. So if I'm gonna go over this solid in cylindrical coordinates, I can rewrite this as equivalently z equals 4 minus r squared. It does work in rectangular coordinates too, it's just a little long. So now if I do that, remember our theorem for these solids says you can take the double integral over the region of projection of the integral from the bottom surface, which was z equals 0, to the top surface, right? This is the bottom surface, the plane z equals 0. The top surface, which was z equals 4 minus r squared, of the density function. Well, the density function was just y. That's what we said, that was given. And then for cylindrical coordinates, it's r, let's call this r, dr, d phi, d theta. And now, if I'm going to do this in r phi theta coordinates, then sorry, dz dr d theta, I'm sorry, dz dr d theta for cylindrical coordinates. Now, y needs to be written in cylindrical coordinates, so that y is r sine theta. Let's replace y with that. And so if I go from z equals 0, then I put 0 here. If the top is z equals 4 minus r squared, then this top is y is 4 minus r. So there it is in cylindrical coordinates. Now I need to write the region R in the polar coordinates that represents the projection. Well, the projection is a circle of radius 2 at the origin. So I just have to let the radius go from 0 to 2 and the angle go from 0 to 2 pi. R times R gives R squared. Then we've got sine theta dz dr d theta. So there was the setup. That's the most important part. But then you have to be able to evaluate the integral too. So we can actually pull this out of here since there's no z in it. We can put it in here and say that this is the double integral from 0 to 2 pi and 0 to 2 of r squared sine theta. And then we're going to take integral of 1 with respect to z, because we took this out, is just z evaluated at 0 and 4 minus r squared dr d theta. Well, that's easy. If z is evaluated at these two endpoints, then this is just 4 minus r squared. So there's the integral. We have to do a double integral now. It's the double integral of theta going from 0 to 2 pi, r going from 0 to 2. 4 r squared minus r to the 4th, multiplying this times this, all times sine theta dr d theta. Okay.
I had a quick question. I had a question about your bounds.
Yeah.
It says that it's an octant 1. Wouldn't that limit you to be from 0 to pi over 2?
Yeah, you're exactly right. I'm not looking at my key. I forgot. Yeah, it also restricted to octant 1. Yep. So what I need to do for this one, let me get it. Yeah, thank you, reference. It was graded that way. I just forgot. Yeah, so we're going to be an octant 1, which means we come down here and over here And this will be solid. The solid is W. I'll take a quarter of this thing. Yeah, so there's W as an octave one. Thank you. And in that case, theta just goes from 0 to pi over 2 instead of 0 to 2 pi. Exactly, yeah. Fortunately, it's not a hard fix. All right. So 0 to pi over 2, 0 to pi over 2, 0 to pi. So this one's not too hard to evaluate. It splits into two integrals. Since these are, right, we can take the sine theta, since it's held constant within the inside integral, and pull it into here. Once it's in there, this is an integral over r with respect to constant endpoints. It's going to come out to be a number. So we can take that number and slide it out of here. And this just reduces to the product of two integrals. The integral from 0 to pi over 2 of sine theta d theta. And the integral from times the integral from 0 to 2 of 4 r squared minus r to the fourth dr. You can do this from calculus 1, and you come out with 64/15. Maybe I should put the 2 over in there. So easy. So this one just comes out to be 1. This minus cosine theta, those two. Okay. This is 1 times, and this one comes out to be at the top end point 32/3, and at the bottom end point 32/5. Whole thing works out to be 64/15. Okay, so there's the first one on the test. Those of you that aren't here tonight, I guess I'll send out your test by email. Any comments on that one before I erase the rest of it? Second one says, suppose u equals 3x plus 2y is a coordinate change. This one's a linear change. B equals 2x minus 4y. Solve for x and y. After linear algebra class, it's a trivial problem, but for us, it's a little more complicated. Let me call those u equals 3x plus 2y. There's lots of ways to do this. So this class, since you haven't had matrix theory, I don't want to write a big matrix. We'll just say if that's equation 1 and that's equation 2, we use elimination to get rid of one of them. Let's take twice the first one. Oops. Twice the first one. And add it to the second one. That'll make the y's cancel. And then I've got 2u plus v equals twice this one plus this one would be 6 plus 2 is 8x plus 0. These cancel. All right, and that tells me that x is equal to 1/8 of this is equal to 1/4 u plus 1/8 v. Let me check it this time. I turned it right. Okay, good. And then someone I can make the x's cancel by taking 2 times the first one and subtracting the second one. So 2 times the first one minus 3 times the second one. That'll give 6x minus 6x. They'll cancel. 2 times this one is 4y. Minus 3 times this one is plus 12 more y. Makes 16y. And then on the right, and on the left, I've got twice u minus 3 times v. There we go. Divide that by 16, and you've got y equals 1/8 u minus 3/16 v. So that's what I was looking for there. Just solve for x and y, those two linear equations and two unknowns. Now I ask you to find the Jacobian. I so wanted to put it inside an integral and have you do an interesting, maybe on the final. it's gonna be too long a test if I did. All right, so the Jacobian in part B. Also written as dxy duv. It's just the determinant. Dx du, dx dv, dy du, dy dv. Partial derivatives. And since these are linear equations, it's real easy, just 1/4, 1/8, 1/8 minus 3/16. The determinant is this times this minus this times this, right? The difference of the product of the diagonal. So 1/4 minus 3/16 plus minus 1/8 times 1/8 came out to be minus a 16. So there was problem number 2. Find the first order transformation of the associated Jacobian. I ask you to convert one of these to polar coordinates. Rewrite the integral to double integral. So given this integral, 0 to 1, 0 to the square root 1 minus y squared, cosine x squared plus y squared, dx dy. This is screaming for polar coordinates, right? Because x squared plus y squared is r squared. That's easier. Square root 1 minus y squared is also easier. So convert polar coordinates and evaluate it. So the way to do this when you have to convert these is to sketch the region. Right? That's the easy way to do this. So what is this? Here I want x to go from a minimum 0 to a maximum 1. So I'm bounded between this line and this line. And then between there, oh, I'm sorry, it's y. Y goes from 0 to 1. Between this line and this line. And then this is the left curve, x equals 0, and this is the right curve, x equals square root 1 minus y squared. If you want to know how that graphs, you square both sides, and we write it as x squared equals 1 minus y squared, together with, since it's that's a non-negative root, you have to have x greater than or equal to 0. And so this is, we just added y squared to each side. It's x squared plus y squared equals 1, the unit circle on the right side. So it's the right side of the unit circle is this one. That's this one, 0 to here, but it's down, it's from y equals 0 to y equals 1, so we leave this part out. So this is the region we're interested in here. And we just want to switch that to polar coordinates. How do we switch that to polar coordinates? We say, well, it's between this ray, this is state equals 0, this one, it's state equals pi over 2. Inside curve and outside curve. Well, the inside curve is r equals 0. The outside curve, since it's unit circle, is r equals 1. Easy. We'll just rewrite that. Theta goes from 0 to pi over 2, the two angles. R goes from the inside function of theta, 0 to the outside function of theta. And then dx dy becomes r dr d theta. Right? This is the little volume element, volume area element in polar coordinates. And then the integrand, since x squared plus y squared equals r squared, we rewrite this as cosine r squared. There it is. And now you can evaluate that by putting u equal r squared. That's a common thing when you see a function of a function in the integral. So you think, what would happen if I let u be the inside function? Then du would be the derivative dr at 2r dr. So 1/2 du can replace the r dr that I see there. I'll put 1/2 du there. I'll put u here, and that will substitute out r. Meanwhile, the theta d theta can pull straight through, and I can rewrite this as the integral of pi over 2 d theta. I can do that because this inside integral is going to be a constant. Points. Then I've got here, well, when r equals 0, u equals 0, and r equals 1, u equals 1, so we're lucky, the endpoints stay the same, and this becomes cosine u and 1/2 du. All right, so there's our calculus 1 problem. This integral comes out to be pi over 4 times the sine of 1. Right? Evaluate this thing. So that's what I was looking for on that one. Or use spherical coordinates to find the volume. Find the volume. I'll leave out the instructions, spherical coordinates on the board. Bounded by the sphere, rho equals 8 above, the cone, b equals pi over 6 below. So if you want to draw this one, got the sphere on top. Here's p equals pi over 6, measure down from the z-axis. And then you let theta be arbitrary, so you rotate it around in a circle like that, and it makes sort of nice. What's the volume of this ice cream cone? Well, it's the triple integral over the solid, call it W, whatever you like, of 1 dV, gives volume, right? When you sweep this out, rho goes from 0 out to the radius here, 8. Phi goes from the z-axis down to here, so phi goes from 0 to pi over 6. And theta goes all the way around from 0 to 2 pi. And then dV, one is just 1, but dV is rho squared sine theta. It's just fun, some of you are better remember that. D rho, dV, that's the integral you have to do. This one, I gave you some nice integrals that split this time. This splits into integral 0 to 2 pi d theta. Since we have all constant endpoints and the integrand is a product of functions of each variable, we can do that. 0 to pi over 6, sine phi dphi, 0 to 8, rho squared, 0. That came out to 2 minus square root 3, 512 pi. Don't want to spend too much time on this integral. All over 3. 2 pi comes from this one. Pi and 2 out of here, I guess. Etc. Okay, one more. Evaluate the triple integral by converting to spherical coordinates. So let's say 5 says evaluate. Integral from 0 to 2, integral from 0 to square root 4 minus x squared. Integral from 0 to square root 4 minus x squared minus y squared. X squared plus y squared plus z squared. dz y dx. So you have to remember what these integration endpoints mean. This means that the top surface is z equals root 4 minus x squared minus y squared, which is equivalently z squared equals 4 minus x squared minus y squared. And by adding x squared plus y squared over, you've got equivalently x squared plus y squared plus z squared equals 4. This is a sphere of radius 2, right? Anyway, 4 to 2 squared. So if I want to put this in spherical coordinates, I'll consider that also rho equals 2. So there's the spherical coordinate equivalent of this mess. Good idea to switch to spherical, right? And then this one is this one says that y goes between y equals 0, y equals root 4 x squared, which is equivalent to y squared equals 4 minus x squared, or x squared plus y squared equals 4, which then yeah. Which says that the region of projection below is that circle. So this is what you have. You have a sphere of radius 4. This is your rho equals 4 top. It starts at the bottom where this was z equals 0, so you're going to go all the way down the xy plane like that. And what is that in spherical coordinates? You can say, well, that is the angle down phi equals pi over 2. So phi will run from phi equals 0 at the straight up to phi equals pi over 2 to smooth out the xy plane. And then theta goes all the way around. So this will be the triple integral. Theta going from 0 to 2 pi all the way around. Phi going from 0 to pi over 2, since the z equals 0 plane has equation phi equals pi over 2. Rho goes from the inside point, inside surface rho equals 0 to the outside surface rho equals 4. And then the integrand, another rho squared. And the volume element, we've been using rho squared sine phi. Phi rho, d phi, d theta. So there was that integral. This one splits nicely into 3 also at 0 to 2 pi d theta. Integral 0 to pi over 2 sine phi d phi times the integral from 0 to 2, excuse me, 0 radius 2. Equals 2. What did I write 4? Anyways, radius 2. Integral from 0 to 2 of rho to the 4th, 0. Okay. And when we get a 64 pi over 5 as a result. Okay, so I hope that was a informative test. Any more comments on that? Is it all right? Well, then tonight we're going to go ahead and start chapter 15, finally the last chapter in this giant book, right? And I do have one section to come back in chapter 14, surface integrals, and that we'll do when we do the surface integrals in chapter 15. So 15.1 tonight, maybe we get to 15.2 a little bit, kind of an interesting section. I think more interesting than this is on vector fields. So this is an introductory section. It's first in the chapter. It's not so bad, I think. What is a vector field? Anybody done these in physics or engineering? Vector field is just an association or a function that associates a vector with each point in a region. Words never do this justice. And it can be a plane region or a solid, I'll just say a region in space. But the idea is, suppose I do this in 2 dimensions. Then the idea is that at each point there's associated vectors. So there's a vector here and a vector here and a vector here. And you can imagine immediately that this has lots of applications. So here are some typical vectors. You can't draw an infinite number of them, so you just draw a few of them. And this might be a velocity field. Maybe there's fluid flowing through the plane. And this, at each point, this is the arrow length tells you how fast, what its speed is, and the direction tells you what direction it's flowing instantaneously at that point. Or it might be a gravitational field, right? At each point, you feel gravity pointing like that. At this point, you feel gravity pointing like that because of various massive objects around here. So that's a vector field. And so we'll just label this F with a vector. And the idea is that each point, let's call this F of x, y. At each point x, y in the plane, those is 2D. You associate a vector in 2 dimensions. 3 dimensions, you can have 3-dimensional vectors at each. Vector is supposed to be the same number of dimensions as the space you put it in. But that's what you're thinking of. It's things like velocity fields and force fields. It can also be electric field, which is sort of almost the same as force, right? Except apply to get the force. Here's a simple example then. Suppose I wanted to sketch showing typical elements, vector fields in the plane. Easier to draw there than in 3 space. A 2I minus 3j. Right? Remember, I is the unit vector in the x direction. J is the unit vector in the y direction. So this also has the notation 2 minus. But the idea is this is a constant vector field. So all the vectors are the same. If you go to any point, like here's maybe 0, 2, maybe. You just draw 2 points to the right, 3 out. 1, 2, 1, 2, 3. And there's the vector at that point. But you go to any other point and it's the same. So when they're all the same length and the same direction, then you gather that this is actually a constant vector field. How about this one? Suppose I said f of x, y is this vector field, x over square root x squared plus y squared, y over square root x squared plus y squared. How about that? How am I going to sketch that? Here's something interesting to note. Since when you compute the length of f, right? What is the length of f? Remember, it's the root sum square of the component. So it's square root of x over square root x squared plus y squared. I put this one up because this one occurs quite frequently in applications. So it's the x component squared plus the y component squared, square rooted. Right? And if you compute that out, what have we got? Square root of x squared over x squared plus y squared. Plus y squared over x squared plus y squared. Oh, x squared plus y squared over x squared plus y squared is 1, right? This is a unit vector field, right? All vectors have length 1. That's easy to draw. And then what about the direction? The direction is at each point x, y is in the direction x, y. It's just scale to have unit length for each vector. So if you're at point XY, when you move in the direction XY, that tells us exactly how to draw this, right? This is a vector field in which, say at 1, 1, I draw a vector of length 1 in the same direction as the vector 2xy. So here's the vector 2xy. I just draw it straight away 1 unit long. If I'm over here, I draw it straight away 1 unit long. If I'm over here, I draw it straight away 1 unit long. So central force here, right? Not force necessarily, but every vector is just a unit vector pointing away from the origin. Because they're right there in the direction of coming from the direction of the vector xy that comes from the origin. Unit vectors away from the origins. But sometimes you notice these have constant length or something, and you can tell their direction by which coordinates they are. That's useful. Here's another one that comes up that's kind of useful. Suppose I said f of xy equals yi minus xj. What's that one? Well, you might look at the length and direction again. The length of f, actually put an arrow over the top, it's a vector. The book will use boldface. I'll put an arrow over the top. That's common on the board, but it's too hard to do boldface on the board. And the book will use boldface, it's easier for that. All right, so but what is the length of f here? Well, it's the root sum square of the components. The square root y squared plus minus x squared. Oh, it's square root x squared plus y squared. It's the distance from the origin. So the length of f is distance is however far it is from the origin. And then what's its direction? So this is the length, however far it is from the origin. What's its direction? Well, since if you dot product this with the vector xy, xy dot this vector y minus x, we get xy minus x by x. It's 0. What does that tell you? It's perpendicular to this vector from the origin to the point xy that you're at. I just said it. If the dot product is 0, that means it's perpendicular to the vector from the origin. So it's perpendicular to the vector from the origin to the point you're at, xy. That tells you how to draw this one. Make its length the distance from the origin, make it perpendicular to the origin, so the vector from the origin. And then you just have to figure out which way. Like for instance, if I put this vector at 1, 1, we know that this distance here is square root 2, so it's going to have that same length as its distance from the origin. But then it's going to be perpendicular to that. So I could go like this, like square root 2, or it could go like this. Which one is it? Well, you just figure it out for one of these. If I'm at the point 1, 1, I get, you can just plug it in also. I get the vector 1 minus 1. So it must be this one over here, not this one. All right, so I just draw perpendicular and square root 2 units long. So I draw that one there. And then I draw the same thing. These are going to be clockwise. If I'm, say, 1, 2, 3 units down, then I draw perpendicular to that 3 units over. Right? 1, 2, 3. And that's what you do. Now you can draw these vectors all over in the plane. This is 1 unit over, then this is 1 over unit that way. And by continuity of this field, when it's continuous changing components, they all have to go clockwise. Otherwise, they'd start. They wouldn't be continuous if they didn't change continuously. So there we go. We get something like that where it's a rotation field. Every vector, it gets faster and faster out here, but the idea is that it all rotates around together, right? This vector, the vector that's 3 times as far away goes 3 times as fast, so just go in a big circular rotation. That's what we got there. A couple others here. Yeah. So those are the kind of things that come up in a lot of applications. There's one more that we want to mention also. It's a central field like that first one we did. but it comes into play in a bunch of forces. The definition, if the force field is a constant over the length of r squared, where r is the vector from the origin. In other words, r is the vector x, y. Write it the same way they do. Anyway, times x, y. There's all about x, I plus y, j. But as long as we're, let's see. Yeah, they just wrote r again. All right, let's just do it the same way. R, where r equals x, y is the vector from the origin to the point here. If that's the force field at each point is whatever point you're at, it's this force field or vector field is said, this is an r squared, it's r cubed, is said to be an inverse square field. The reason being that the length of f is what? Right, this is just a number. So remember, the length of a vector is the number, the absolute value of the number, times the length of the vector that multiplies it, which is just r. So from your theorems for a constant times a vector, the length of a constant times a vector is the absolute value of the constant times the length of the vector. That's where I get that. Now r over r cubed gives you r squared, and so what you get is the absolute value of c over length of r squared. Oh, no wonder it's called an inverse square law. It's inversely proportional to the square of the distance you are from the origin, like gravity. For gravity, for instance, c is equal to minus g m, where g is the gravitational constant. Capital M is is one body, such as the sun, and little m is the other body that's being attracted, such as the Earth. And so this is how you do it with gravity, for instance. Also, the electric charges, then C would be 1 over 4 pi epsilon naught, as I recall. So those two forces, at least, look like this. The object is to recognize, oh, that's a central force. Again, since if you put, going back to that first example, since this is just a number times r, its direction is towards or away from the origin according to whether c is positive or negative. So vectors, since they're proportional to r, number times r, where r is the vector to the point you're at. So they all point towards the origin if c is negative, such as in gravity, or away if c is greater than 0. You have two charges, both positive, and they push away. All right, so that's the simple stuff there. Have another definition. Since it's starting a chapter, it's lots and lots of definitions. That means it's not too hard, but it's lots of writing. We'll say F a vector field in the plane. And again, this all extends to higher dimensions, but I'll do it in the plane so I don't have to write as many letters. And that's what the book does too, really. F is called a gradient field. And these are going to be very important to us in upcoming sections. There's lots of applications in the world where this comes into play. F is called a gradient field if it's a gradient. If F is the gradient, let's put the letters in, F of x, y, gradient of a function phi of x, y. Remember the gradient before, where this upside down delta called del denotes the vector with components d dx, d dy. It's the vector partial derivative. Yeah, this is the beginning. Hence, it's called a gradient field because all it's at each point it's a gradient. We call it a gradient operator sometimes because it takes functions to functions. Okay, and then I'll introduce something a little early. I don't think they put it in the book yet, but this is leading into this. If F is a force, this doesn't have to be a force. It could be a velocity field or an acceleration field or something like that. But if it's a force in particular, a force F is conservative, or that is a gradient field is said to be conservative. So lots of writing, like learning a language tonight. That's what conservative forces are. Gravity is a conservative force. Electric field attractions is a conservative force. So those are very important applications of that. All right, so here's this one. Oh, and in this case, phi is called the potential for F. Phi such that F is the gradient. It's a potential for F. All right, so here's an example then. Show that this is absolutely trivial. Arctangent xy is a potential for the function f equals y over 1 plus x squared y squared x over, this is x times y here, I should have put a comma there, 1 over 1 plus x squared. Okay, how do you show that it's a potential? You just take the gradient and see if you get f. There's nothing more to it than that. We would say since the gradient of the proposed potential arctangent of xy is what? It means take d dx, d dy, and operate on the function arctangent xy. I keep putting that comment in there, don't I? arctangent xy. Geez. All right, it means take d dx of arctangent. And d dy of arctangent. Okay. Well, what's the derivative of arctangent xy with respect to x? Partial derivatives in the beginning of the semester, right? Think of this as u, right? Derivative of arctangent u with respect to x, we recall, is 1 over 1 plus u squared times partial of u with respect to x, right? Partial of arctangent u with respect to y is 1 over 1 plus u squared times partial of u with respect to y. That's just a chain rule for partial derivatives there, right? The arctangent u to u, du, dy. Arctangent u dx, du dx, u du dx. So what is partial of u with respect to x? Oh, it's just y. Partial of u with respect to y is just x. And so sure enough, you get back what you have there. You get y over 1 plus u squared, but u is xy. And uy is x, right? Partial of xy with respect to x is, with respect to y is x. Over 1 plus u squared is 1 plus x squared. Sure enough, gradient of this function is this vector value function, or vector field, called both. So that does it. This function, phi of xy, is the potential for this vector value function, f of xy. Moreover, there's some important operations you want to be able to do with these things. Now that we have this gradient operator, d dx, d dy, we can also use it with vectors. So some more definitions. The divergence of a vector field f is the gradient dot f. So you can take the gradient of a function, right, by just applying d dx to the function and d dy to the function to get a vector, but you can also take the dot product of a gradient with a function. We'll call that the divergence of that. And interestingly enough, if you take the gradient of a function, you get a vector, right? But if you take the divergence of a vector, you get a function, because this dot product is going to give you a function, right? So that's going to be the divergence. And there's another thing we can do with vector value functions or vector fields. The curl of a vector field f is del cross f. Right? Since del is a vector operator, you can cross product it with a vector of 3 dimensions. These both. This one only applies in 3 dimensions. The dot product applies in any number of dimensions, 1, 2, 3, 4, 5, forever. This one only applies in 3D because the cross dot product is only defined in 3D. But we'll also give it this notation, curl f. So divergence of f is a function, we call it a scalar function sometimes, but the curl is a vector value function. So you take a curl of a vector value function, you get a vector value function. All right, and so there's lots of properties that go with those that are kind of obvious from the notation, which is good because that way you won't be someone to typically make mistakes. I gave you a few proofs of the problems just to be familiar with those. For instance, so these have expected properties mostly. Some of them are a little tricky, but not many. Such as Suppose I wanted to take the divergence of the sum of two vector fields. What should that come out to be? You can probably guess what it is right off. We can prove it right here, right? But you just think of this in your mind. What is this? This is d dx, d dy, dot product with f, f1, f2 are the components of f, let's say, and g1, g2 are the components of g. What do you get? Well, you can leave this out here and add these together component by component. So you're dot producting with f1 plus g1, f2 plus g2. And now, by the definition of divergence, we take d dx of this plus d dy of that, and we get a scalar function. So we got d dx of f1 plus g1. All right, this operating on this plus this operating on this, that's the dot product. Plus d dy of f2 plus g2. And then you notice that this is actually just the f1 dx. By linearity of this one, you get d dx of f1 plus dx of g1, so plus dg1 dx. This derivative over here, and then d dy of f2. So this one, and I'll put this one over here, plus d dy of g2. But wait a minute. This one's divergence of f, and this one's divergence of g. So this is I should put this up here. Divergence of f plus g is equal to this, right? This is how you write the divergence, the gradient dot, whatever vector function it is. And then this one is divergence of f plus divergence of g. So as you might have guessed, the divergence of the sum is the sum of the divergences. Right? So a lot of them are like that, and they're tedious to prove all of them. I just wanted to show you how they go. You do the other ones just like that. Most of them. Now, some of them are a little harder. Maybe I should do one more and that's a little harder. What is a rule for divergence of a scalar function? P times a vector value function. Wonder what that is. All right, we can figure it out. Divergence means del dot, so we're taking del dot F. And then phi is a scalar field. It's just a, this is like taking a scalar, a number, and multiplying it by a vector. It's just that these are both functions of the coordinates, so you're doing it in every coordinate. And so this is d dx, d dy dot phi f1, phi f2 is the scalar phi multiplying the vector f. It's just that these are functions of the coordinates, so now you can take d dx and d dy of them. The divergence means d dx of this one, so it's d dx of phi f1 plus d dy of the f2, right? This one, two. And now you have a product rule in here, right? So it's d dx f1 plus phi f1 dx plus by the product rule over here, dp dy f2 plus right derivative of the first times the second plus first phi times derivative of the second. And now you can see what this comes out to be. If you pull these two together, you can say that this is equal to phi times the f1 dx plus the f2 dy is the divergence of f, right? That's this one, right? Phi times the f1 dx plus the f2 dy. And then the other two, they come over here, and you say, oh, this is gradient of phi dot product with f. Right? Gradient of phi would have components d phi dx, d phi dy, and you dot product with the vector f1, f2. Maybe I should put one more step in there. Should I put one more step to make it? Maybe I should. Let me put one more step. So I take these two, phi times the f1 dx plus the f2 dy plus phi dx phi y dot f1 f2 is these two terms, and now this is phi times divergence of f plus gradient phi here dot f. And so there's some other not so obvious rules like this one. You have the divergence of the scalar times f, it has this right up. One very important property that's used in a lot of these applications is this one, and you might guess what this one. But here's a theorem. That's a theorem too, but I won't write it such because it's not. But here's another theorem: divergence of the curl of f is equal to 0. How can that be? So, because this is divergence means take del dot, curl means take del cross, and you can kind of see it here. I mean, it's natural. Remember, if you take A dot A cross B in calculus 3, what did you get always? You always got 0 because this is perpendicular to A and B, right? But if it's perpendicular to A, then the dot product with A is going to be 0, right? And so this thing holds this. The way to do this is to write it all out. But if you do this, repeating del also has the same effect. This one, however, is in 3 dimensions. So this one I have to put ddx, ddy, ddz dot del cross f. This is dx, dy, ddz cross f. And what does that come out to be? Remember this from calculus 3? What is this? This is the scalar triple product, right? You take the cross product here, and then the dot product of that is the scalar triple product. Remember that if you take A dot B cross C, what does that come out to be? You can only take it in one order, so you don't need the parentheses. Dot product, and that's just the number. You can cross product, so it has to be in this order. But I'll put the parentheses in for clarity. What does that come out to be? Remember that one? How you could evaluate the scalar product? It had this nice determinant formula. Put A in the first row, B in the second row, and C in the third row, which is the determinant. This is always the determinant of A, B, C. By way of recall. I'll say recall that. The same thing applies here since it's a dot product and then a cross product, because you apply that proof there and you say this is actually the determinant ddx, ddy, ddz, dx, dy, ddz again because it's the same vector. Maybe if you took linear algebra, you'd call when you repeat a row as a determinant. Determinant's always 0. And then F1, F2, F3, because F has 3 components in 3 dimensions. And now if you compute this out, just compute the determinant, I'll say dot, dot, dot. You get 0, and it's because these two rows are the same. Right. So there's the proof, except for a few boring computational steps to show that two rows can identical give determinant 0. The proof that divergence of the curl is 0. All right, so there's some proof similar to what I'm asking you to do this time. We also want to be able to compute a couple of computational examples here. With that, I think, yeah. All right, so how about this one just for a computation? Because, yeah, I mean, these things, you can see all the definitions, but until you actually see one of these things, it's like seeing the definition of a dog. You've never seen a dog before. It doesn't, the words don't do so much for you, right? Find the divergence of F and curl of F. This really illustrates it a lot better to you actually see it. If F is the vector field with components x squared I minus 2j plus y vk. All right. So we'll call this A and call this B. What's the divergence? You compute it like this. Divergence F, all is del dot F, gradient dot F, is, this is in 3 dimensions, so it's ddx, ddy, ddz, just put the number of components according to the number of dimensions in, dot, and we'll put that one in here. I'll change the notation. It's x squared minus 2 yz. I'll put my z with a bar in it so you can distinguish the two. All right. And so the divergence, right, the dot products take this with this, this with this, and this with this, and add them. So it's ddx of x squared plus ddy minus 2 plus dz of yz. Partial of x squared with respect to x is 2x. Partial of negative 2 with respect to y is 0. And partial of yz with respect to z is just y. So it's just 2x plus y. And what you observe is that the divergence of a vector field is just a scalar field, function, an ordinary function. Right? That's what a scalar field is. It's a function on the whatever region the vector field is defined on. So the divergence of a vector valued function x squared minus 2 yz is just this function. How about the curl? Curl of F means you take del cross F, means that you take ddx, dy, ddz. Cross product with F is x squared minus 2 yz. Remember how to take the cross product? There's a nice fast formula, but the one that's easy to remember is to put it in the determinant, right? Determinant formula for computing the cross product is probably easiest for us. So we'll just put I, J, K in the first row to compute a cross product, right? And then we put this one in the second row and this one in the third. You have to put them in order. They'll be off by a minus sign. Put the first one first. ddx dy, ddz goes in the next row. And then x squared minus 2 yz. Right. Gotta get rid of this. So now, remember how to compute determinants. You take this one times the subdeterminant got by wiping out its row and column here. So it's time to determinant d, dy, dz minus 2yz. And then minus j times its subdeterminant. Wiping out its row and column. So plus minus plus. Wipe out its row and column. You got ddx, ddz, x squared yz. ddx, ddz, x squared yz. And then plus k times its subdeterminant. Plus minus plus. Wipe out its row and column. We get ddx, dy. X squared minus 2. There it is. And then we'll put all this together. This one will get a vector, right? Divergence of a vector field is a scalar field. Curl of a vector field is to get a vector field. All right, and so we take I times dd of yz is z. Taking this with this, partial with respect to y of yz is z. Minus this times this, so it's minus root of 2 is 0. And then minus j times ddx of yz is 0 because y and z are treated as constants. Minus ddz of x squared is also 0 because x is a constant with respect to that partial derivative. Plus k times ddx of minus 2 is 0. Dy of x squared, well, x squared is treated as a constant, it's 0. This one is actually just the vector zi. It's a vertically pointing vector, proportional to how far you are from the xy plane. There's the curl of the vector. These have important consequences for rotation and for sources. If something's flowing out, you get a divergence. If it's rotating, you get no divergence. If it's rotating, you get a nice curl, but if it's coming out from a source, you get 0 curl because divergence of the curl is 0, right? So these are some of the physical significances when we apply these. All right, well, it says it's about a minute left, so let me write the homework problems out. And these aren't too hard. I don't think you'll find them difficult. You just want to be able to do gradient, divergence, and curl, and prove a few of these simple properties. Be able to sketch the vector fields, right? What an inverse square field is, and what's a conservative field. This one that's a gradient. All right, so 15-1, look at problem one. Look at 5, 6, 7, 8, all of them. Look at, I left one of these out. I'll just leave it in here. 11 to 37 odd. Okay. Then we'll meet next time. We'll start to do some real interesting stuff. I had some nice overheads here, but I have to put them off till next time. We're going to do line integrals. Make sure you're here for that. Thank you.
Professor,
Yes.
when is the final gonna be exactly?
It's listed on the syllabus. It's according to the schedule of classes, and I don't remember what the final is exactly.
So it'll be following the syllabus?
Yeah, it's on the syllabus, and it's also according to the schedule of classes.
Okay.